again to Radical Talks. This is a podcast from AIVC Radical Ventures in which we explore what else but the AI era. We dig into the innovation happening at the forefront of AI, the cutting edge research, the new product paradigms, and of course, the startups building at the frontier. I'm Molly Welch, and I'm a partner here at Radical. So let's get into it. We've got a really special episode today. One of our focuses on Radical Talks is really kick-ass startups that are at the forefront and frontier of AI. And this week, we've got a super special one in that vein, and that's P1 AI. P1 is a startup that is developing artificial general engineering intelligence. We talk a lot about AGI in the world of AI, and including on this podcast, and how AGI is going to transform the world of bits with hyper-intelligent software. This is super cool. We love the world of bits. Don't get me wrong. But this transformation really begs the question, what about the world of atoms? And that's the question that drives P1. P1 is building an agent for designing physical systems. Their agent has a wonderful nickname, Archie, sounds quite intelligent, and can perform basic engineering tasks, much like a junior engineer, an intelligent junior engineer. P1 wants to put Archie in the hands of every industrial company on Earth, enhancing team productivity and ultimately helping us design things that we have only dreamed of to date. So we're super lucky. We have co-founder and CEO of P1 here on the podcast, Paul Eremenko. And I was just saying to Paul, he might get mad at me for saying this because he's very humble, but Paul is kind of the Tony Stark of AI. He is a legendary engineer and engineering leader. He is the former CTO of Airbus as well as United Technologies. He spent several years at DARPA and at Google as an engineering director. And he's brought really an amazing team together for P1. So Paul, we're really excited to chat and welcome to the podcast.
Thanks, Molly. You're far too kind. Happy to be here.
So, Paul, you've had this amazing career and you're on an exciting new mission with P1. Walk me through your career and your path to startups. How does the Tony Stark of AI become the Tony Stark of AI? Tell us.
So I grew up as a computer nerd and a space cadet, and soloed in an airplane before I was allowed to solo in a car, and was always just really taken with aerospace engineering because you got to build things that were the bleeding edge of complexity, the bleeding edge of what we know how to do as a civilization, as a human species. And so went to school for aerospace engineering, and very early in my career became interested in how do we manage that complexity, right? So how is aerospace different than other engineering disciplines? Because most of the products require hundreds, if not thousands, of minds to come together in order to design them. So how do you organize them? What are the systems engineering methods, the design tools, the workflows, et cetera? And in the late 2000s, I ended up at DARPA, and had the opportunity to start DARPA's Advanced Design Tools and Advanced Manufacturing Program portfolio. This was just in the wake of the Joint Strike Fighter being fielded, the F-35. And the F-35 was the most expensive program or product or whatever you want to call it ever developed by humanity, right? And this is cool, but also very problematic, because if you plot the curve of the fighter jet costs going from the F-16 to the F-22 to the Joint Strike Fighter, it's a very steep exponential, and it's just not clear how you afford the next one. And so the question du jour, which actually still is the question du jour in the Pentagon, is how do you break the cost curve on these things? And my proposal was basically, let's try to do what we did in semiconductor design, which is introduce design automation techniques. And can we do that for these much, much bigger, much more multi-physics, much more heterogeneous systems like airplanes? And so DARPA took this very seriously. We invested something like $500 million over 4 years into this effort. And it was largely successful. I mean, we learned a lot about how do you scale up compositional model-based synthesis to these very large, very multi-physics systems. And then I spent much of the rest of my career to date applying what we learned from those DARPA efforts in a variety of different contexts. First at Google and Motorola, where I worked on design to order mobile devices. And then at Airbus and at United Technologies, began applying them to airplanes. Probably my proudest career accomplishment up to that point was at Airbus, really turning Airbus engineering into a model-based enterprise for the next airplane. And then coming out of the United Technologies Raytheon merger, I saw unrelated, but saw an opening to possibly make hydrogen airplanes a reality. Hydrogen airplanes had been sort of a dream for many, many years since the dawn of aviation, and pounced on that idea with a couple of Airbus and UTC alumni. And so that was my first foray into the startup world.
Super cool. And it's fascinating to hear how those early DARPA questions, how incredibly relevant they are today, and how incredibly relevant they are also to P1, right? To the mission you're focused on now and the animating principles and problems for the company. So with that context, tell us a little bit more about what inspired you to found P1. How did you come to this idea? What got you excited and what convinced you to take the jump?
Yeah, in the early 2020s, I saw the deep learning revolution to really, really start to take off, really start to unfold around me. And even though I was working on something completely different, hydrogen, I was curious. I had always been AI curious, if you will. And so I was like, well, look, I grew up on hard sci-fi, and clearly as AI becomes more intelligent and eventually turns into superintelligence, clearly the biggest application is to the built world, right? Is building stuff and ultimately building starships and Dyson spheres, right? And so I was like, who's working on it? I'm doing something completely different, but I want to meet them. And the answer was crickets, is that nobody was working on it. And today in 2025, the answer is still that there are not very many people working on it. And a lot of what the AI universe is investing in is some is very worthwhile, which, things like drug discovery and medical diagnostics and software engineering, physics and math they're improving. But really, there's not a lot of people, and certainly not the frontier labs, who seem to be looking at the question of, well, where's the AI that's going to help us build the built world, make the built world better? Because ultimately, at least for now, we as humans live in the physical world. And so making that physical world significantly better is probably a first order impact on the human experience. And so that was really the inspiration, is since nobody was working on it, I asked the question, first of all, why is nobody working on it? And then can we solve some of those impediments and do it? And so that's the genesis of P1AI.
Yeah. So you put your hand up, thankfully for all of us. And maybe before we talk about what Archie does, which I do want to spend some time talking about, why aren't there more people working on this problem? In your description, it makes so much sense, right? We're transforming the world of bits with hyper-intelligent software. We live in the built world, in the constraints of the physical systems that we've designed and operate in our physical environments. Why aren't there more people working on this problem and transforming the built world with modern AI? Why is that?
I think it's not for lack of inspiration or lack of desire. I think a lot of the AI leaders grew up on the same hard sci-fi that I did. The issue is the lack of training data, right? If you want an AI engineer to be able to resize the wing of an Airbus A320, for instance, and you say, hey, engineer, make the wing 10% bigger, it really needs to have seen millions of different airplane designs with different wing configurations and different wing sizes in order to be able, as a neural network, to generalize and infer what the impact would be on the design. And there just haven't been a million airplanes ever designed in history since the Wright brothers, right? We're many orders of magnitude off. There's probably order 1,000. And that's true in almost every product domain, is the training data sets, even if you had access to every product design in a given domain, that data set wouldn't be big enough. And then, of course, there's the more practical issue of the fact you tend not to have open source designs that are available on the open internet. You would have to negotiate to get whatever data you could through proprietary channels. So the lack of training data, I think, is really the first order impediment to AI for physical systems.
Let's take that as, kind of one of the areas to dig into. How are you thinking about this with Archie? How do you get around this training data challenge? And maybe more broadly, how are you going about building Archie? What makes it hard to do this? How are you tackling some of the hard stuff? And what are the kind of key inputs to making Archie work?
Yeah, so the first order one is the training data. And so I sort of asked the question, okay, if you want to build an AI aerospace engineer, where do you get a million airplane designs if there haven't been? I said, well, actually, I kind of know the answer to that question because a lot of this model-based engineering tools and model-based design tools are a way to synthesize designs that are provably or demonstrably correct by construction and doing it in a fairly computationally efficient manner. So I said, hey, I know the people in the world, there are not that many of them that probably could synthesize a million airplane designs. And of course, there are a lot of interesting questions about, so a million airplane designs is still not nearly enough to fully sample the entirety of the design space. The design space is humongous. And so how do you sample it? You want to sample densely around the dominant designs because a lot of the engineering happens as small perturbations to existing designs. But you also want to sample the corners and edges of the design space because that's where innovation comes from. Or maybe you want to learn why you don't want to go into a certain corner or edge of the design space. So it's not just about the using these kinds of design tools to create the designs, but it's also picking which designs to sample in order to create the training data set. That's kind of the first order problem that we set out to solve. And I think we have convincingly demonstrated that we can solve this physics-based supply chain informed synthetic data problem. And then the question is, okay, so you have a million airplane designs and you have a performance vector associated with each of those designs. If you just throw that at an LLM, it does not magically become a good engineer. Shocking, right? I know. You still, quantitative reasoning, spatial reasoning, these are not things that LLMs are inherently good at. And so you have to choose models that are purpose built or purpose trained to be able to do a lot of the engineering reasoning functions and then make all of those models work in concert somewhat harmoniously and deliver a user experience that's fairly seamless, that is roughly equivalent to that of a junior engineer.
So not trivial to build this. I mean, and that's one of the answers to why are there not ubiquitous Archies in every industrial organization on Earth. This is not simple to do. So really helpful to hear how you're approaching it and the P1 approach. Tell us a little bit more about Archie. So what does Archie do? I understand there's the capabilities of the junior engineer that you are trying to emulate. What does that look like from a product perspective? What's the hope for what Archie can do and where is the product today?
Yeah, first from a scoping perspective, we wanted to bound the problem, right? So the thing that we are not trying to build out of the box is some kind of engineering superintelligence that can just solve every engineering challenge about a physical product, because frankly, that's also not what human engineers do, right? Human engineers are good at a very specific set of things. Roughly speaking, what they're good at is taking the full set of requirements, picking the key design drivers out of those requirements, coming up with a handful of possible solutions to meet those key design drivers, doing first order sizing of the design, and then picking the right tools and knowing the range of validity and the range of applicability of those tools to do further detailed design analysis as you progress through the design process. That's what humans do in the engineering design process, and they interact with a huge ecosystem of tools. When I was at Airbus, for instance, we had somewhere between 700 and 800 tools in active use and several thousand tools in the overall engineering ecosystem, right? So it's a very complex landscape, and we are in no way trying to replace or even improve or even automate any of those tools, right? The tools are there, the humans interact them, and Archie should interact with them. But what Archie does do is the cognitive automation of those other tasks, right? Picking key design drivers, doing first order design sizing, and then picking the right tool to use. So that's a much more manageable problem. And as it turns out, actually, the vast majority of things that design engineers do are fairly reducible to a few primitive operations. So it may be a very complex chain, kind of like a chain of thought or chain of reasoning, but that chain of reasoning can be constructed from a few primitive operations that we then need to get our menagerie of AI models to be good at solving.
And how do you think about evaluating how good Archie is at these various tasks? The challenge in LLM-based systems generally, evals are notoriously difficult and imperfect for evaluating capabilities of LLMs. And I'm curious how you're thinking about it on these physical engineering tasks. How do we evaluate success for Archie?
Yeah. No, it's a really good question. And it was actually one of the very first things that we had to tackle was to know whether even changes that we're making to the training data or to the inference architecture, are they making him better or are they making Archie worse? And sure, there's kind of a vibe test that you can do by just interacting and seeing how it does on various queries. But we took a much more systematic approach so that we could really instrument this set of experiments and built a set of engineering evals. We call it Archie IQ. And it's basically a battery of questions. We adopted a framework from human cognitive psychology called Bloom's taxonomy, which kind of ranks the cognitive difficulty of various problem solving tasks, and use this taxonomy to create a test that a human could take and get a score, which would give us a kind of a human reference point. And you can have humans at different levels of expertise. So a junior engineer, average engineer, expert engineer take the test, and then have Archie take the test as well. And we can compare Archie against different versions of Archie. And we can also compare Archie against a human. And we, in fact, have written this up because I think this is the first real cohesive attempt at a framework for evals for physical systems engineering.
You have big ambitions for P1. We talked about sort of the sci-fi inspirations and origins of the company and of the company mission. But you also have more short-term pragmatic focus and orientation at the company from a commercial perspective and a product perspective, which I love and I think is phenomenal. Can you tell us a little bit about how you decided, where you decided to start in the world of physical systems and why that starting point was compelling to you?
We decided to start with data center cooling systems. I think first and foremost, there's a certain poetic elegance to it, right? It's an AI designing its own cooling system
I love it.
to let itself scale, right? So there's certainly that, but kind of on a more tactical level, the beautiful thing is, I mean, these are industrial chillers, basically. They are very multi-physics systems. So they have fluid flows, right? Refrigerant flows. They have air flows. They have an electrical component to them. They have thermal interactions, vibrations, acoustics, et cetera, right? So very, very rich in terms of the physics domains that the system covers. But the level of complexity is pretty manageable, both because the unique part count is like order 1,000 versus, say, an airplane, which is more like order 1,000,000 unique parts in the system. And also the physics in a chiller are fairly linearizable. So when you talk about airflows, you're talking about a one-dimensional flow through a duct as opposed to a three-dimensional viscous compressible flow over a wing. So in terms of generating this physics-based synthetic training data that we create, it's a fairly manageable problem. So we wanted to start with not the hardest, but the manageable. But it is also a fantastic market opportunity because a lot of the players in the space, these are legacy HVAC industrials that are now tackling this exponentially growing market of data centers. It's a real pain point for them to cope with the growing demand. So lead times on cooling systems are sometimes now rivaling the lead times on GPUs, right? So it's a very acute pain point for the customer, and it's a great use case for us with traceability to the big systems like aerospace and defense. But that's pretty manageable for us to get a product into the market.
Manageable technically, commercial tailwinds, and poetic. It's a killer combination.
That's right.
I love it. I love it. And of course, there are these bigger ambitions for the company. You've talked about Dyson spheres and starships. We started there. What's the moonshot physical system? Maybe it's one of these that I just described that you're really dreaming to design with Archie.
Well, it sounds like a leading question, Molly. If you call it a moonshot, you're going to the moon,
It
right?
is, I'm sorry.
That is what a moonshot is, quite literally.
You can choose something else too. I've led you there.
I think the progression for us is first to tackle the built world, right? And the terrestrial built world, if you will. So we can springboard from industrial cooling systems to broader building systems, industrial systems, so things that go into a factory, all of the equipment such as mills, lathes, equipment handlers, robotic arms, right? Those kinds of things. And then move into the mobility world. And the mobility world for us is automotive and mining and agriculture and ultimately trains, planes, and automobiles. And then, of course, the dream is sort of aerospace and probably some unique defense applications as well.
Very cool. And really inspiring moonshot visions, literally speaking. Maybe to break script for a little bit, I know we didn't talk about this, so I'm sorry to throw this one at you, but you've had these really amazing experiences in government, in large engineering organizations, and for the past several years, you've been in the world of startups. What's the most surprising piece of startups, of the world of startups, compared to perhaps your experiences at a Google or a DARPA or at an Airbus? What's really surprised you about the startup ecosystem?
Let me give you two. Let me give you a good one and a bad one.
Yeah. We want to hear it all.
Um, yeah, I think the good one is just the quality of talent, right? The smartest people in the world seem to be in this ecosystem, and they are unencumbered, right, by the webs of company politics and all of the other things that you see in big companies and government labs, et cetera, right? So I think the intellectual sort of liberation of this ecosystem is just phenomenal, and it's freeing, and it's just wonderful.
Mm.
The flip side of it, I think, is, and this is not a dig at anybody in the current conversation, um, but is that the investor ecosystem is very risk averse in my experience,
Mm.
right? And there's actually a very small sliver of venture capital that is equipped to take real technical risk and truly be intelligent investors in deep tech.
Yeah.
Right. So I think there is this general view of like, oh, venture capitalists are like the most innovative people. Well, some are, right? And certainly gratified by present company and Radical's philosophy on this. But in general, I was very surprised and remain surprised and astonished repeatedly by the scarcity of big technology vision and
Mm.
risk tolerance for the big deep tech bets.
It's really interesting. And yeah, we're very proud to be oriented really towards these deep tech, technically risky ideas at Radical. That's what gets us excited. But you're right, that's not necessarily everyone in the venture world. Do you think that's changing? There's so much conversation now about critical technologies and even US competitiveness. Do you think that attitude towards deep tech and frontier technologies is starting to change as the macro environment shifts?
I think perhaps it is. I'm not sure I know the answer to that.
Yeah,
I think the challenge is that it's not enough to just be like, okay, I am now a deep tech investor, right?
sure.
You also have to understand the tech and have a vision, right? And have a framework for making
Yeah,
these kinds of so just throwing dumb money at hard technology isn't the solution either,
yeah,
right? I think what is rare is the vision and the intellectual framework for making those investments
yeah.
intelligently.
Yeah, totally agree. And that's what we hope to do here. So it's a good a
That's
good
right.
challenge.
Well,
And for
that's
the
that's why we're
VCs listening.
that's why we're here. That's why we met, right?
Exactly. That is exactly why we met. Kindred spirits in that sense. And speaking of kindred spirits, we are both sci-fi fans, and this is a piece of nerddom that I hold close to my heart and sometimes close to my chest. Although in San Francisco, they're all kind of weirdos here, lots of sci-fi nerds as well. What's your favorite sci-fi story and why?
Well, I feel obliged to plug the namesake of the company,
Yes,
right?
exactly.
Which is a book by an unknown author, one hit wonder as far as sci-fi goes, Thomas Ryan. Then the book was called The Adolescence of P1, which is P1 is the AI in the novel and who we named the company after. And it's really one of the first, 1977, I think it was published, and it was really the first depiction of an AI that becomes sentient, right? And it's a complex picture, let's put it that way, right? So it's not unequivocally good, it's not unequivocally bad, but certainly interesting. And the book happened to just be personally meaningful to me because I found a copy in, I think, my junior high school library, and it
Mm,
was already dated at that point, but it just stuck with me through many, many decades, and it was kind of an eye-opening inspiration for me. It's not necessarily the greatest literary masterpiece, but I think it has its place. I think it has its place in history.
I love it. And the adolescence of P1 is a nice framing for this stage of the company as well.
Exactly.
The early journey of P1, and we're very fortunate to be on it. And we will also, we're, I think, committed to the mission of flipping the script. And in the story of the adolescence of P1, there's complex ending. P1 doesn't end up being the most lovely and friendly system. So we'll flip that script together in
That's right.
in the adolescence of P1 here on Earth in startup land.
I
So
th I
yeah,
think the story is that is we can build the future that we want, right? We don't need to be
yes,
scared of the future. The future is not a thing that happens. The future is a thing that we build together. So
I love it. I love it. What a perfect place to end it. Paul, thank you. Thank you for coming on. This was a blast. We really appreciate it.
it's my pleasure. Thank you very much, Molly.
That's all for Radical Talks this week. If you had as much fun as we did, don't forget to subscribe wherever you get your podcasts, and we'll see you for future episodes. See you then.